L is the unit interval, is classical, typical fuzzy sets. Of course, I will extend the order of the L to the functions, point-wise definition, making fuzzy sets, and I will extend the negation in L to the negation of functions. Of course, if L is a transitive reversing system, this is a transitive, and reciprocally, because it suffices to take the constant functions. Taking is a usual trick in fuzzy logic to take constant functions. You know, because the 0-1 interval is distributive for minimum and maximum, the functions are distributive. But if the functions are distributive, just take the constant functions to prove that 0-1 is distributive. It's the same. Okay, this will allow us to interpret fuzzy. Then, of course, this is more less obvious. If the ground set is type 1, the functions are type 1. If the ground set is type 2, the functions are type 2. Extending, of course, the operation also pointwise. Then, this the fixed transitive reversing system, this verifies the principles. If and only this extended with any x, also verifies the principles. It's the same to say this is type 1, that this is type 1, type 2, type 2. But anyway, we have type 1 and type 2. If this verifies non-contradiction, this also and reciprocal. It is the same property in the ground that with the functions. The case with the ordered unit interval is curious because we can characterize type 1 and type 2 operations. It's not difficult. Look, imagine that F is an operation. This operation is type 1, taking a strong negation, this is strong negation, if and only if verifies this network. Look at just one variable, and just one. This is the fixed point of the negation. F doesn't need to be a determinant, is any function verifying. Of course, there are thousands. For what concerns type 2, in the same structure, the situation is that. Look, this number, the fixed point of the negation, separates type 1 operations from type 2 operations. Separated. This happens, as far as I know, only in the 0-1 interval. In the particular case, it is very frequent of taking the classical 1 minus x negation, 1 minus identity. The type 1 operation is those that are bounded by 1/2, and the others are bounded by 1/2 below. Then, in that case, it is 0.5, the element that separates type 1 from type 2 operation. Of course, the theorem on the principles is not a characterization. I am not forced to consider only type 1 and type 2. I can manage other operations. Then, following the theorem I showed you 5 minutes ago, if 0 verifies a non-contradiction, any f less than if 0 verifies the non-contradiction. If an operation excluded middle, any function greater, this is here, this is a mistake, greater than g also verifies the excluded middle. Then in the case of the unit interval, everything is clear. The sum verifies that because a plus not a is 1 divided by 2 is 1/2. This is just the operation that is in the border of the two classes. Of course, then all operations that are smaller than the arithmetic mean do verify an NC, and those operations that are greater than the arithmetic mean do verify the excluded fundamental principle. Then, between min and max, we should place in the middle point, just in the arithmetic mean. Okay? Mean, arithmetic mean, max. That is just the central point of the interval minimum may be, maximum may be, that gives the separation between those that verifies non-contradiction and those that verifies exclusive. This is very easy. Of course, operations verifying that all p-norms, but other functions like that. Verifying that, of course, all piconorms, and that, and then look at in this case, in the case before, it was a phi minus 1 or 1/2 that separate those that verifying non-contradiction from those verifying exclusive middle. Now, without type 1, type 2, is the arithmetic mean, the operation who separates those verifying non-contradiction from those verifying exclusive middle principle. Okay. What for the case of multiple value logics? Well, I did never study the case. I started with Professor Morada, he's now in Chile, a paper on the special case of multiple value logics. But of course, multiple value logic usually take the truth values in a subinterval, in a subset of the unit interval. For example, in the old Lukasiewicz case, 0 false, 1 true, 1/2 undecided. Then the values of a multiple value system logic is value numbers between 0 and 1. Sometimes a finite collection of numbers, sometimes an infinite collection of numbers. For example, the classical system, the first one that defined Lukasiewicz, this is the set of truth values, intersection of U with mean, union with max, negation with and the order of these elements is just the order in the real life. Of course, in this case, you have non-contradiction and exclusive middle. What happens if that, because of that deserves a close study, what happens with with other systems of multiple value logic? That sometimes the knot is not defined by 1 minus x, and sometimes the order of 0, 1/2, 1 is not taken linearly. Then I should study the more or less 20 different systems of multiple value logic that are in the books, which ones are inside my model and which ones are not inside my model. I never did that. I just started to do it a couple of weeks ago with okay, let's go to our end. Standard algebra of fuzzy sets, of course they verify non-contradiction is clear after the results. But standard algebra of fuzzy sets are not the only algebra of fuzzy sets. It's a very particular case, that is the case used in the application of fuzzy logic.